Question 14, book number 1, based on the 2020 NEC, and it's electricaltime.com. A piece of utilization equipment that is not a motor and will operate for 15 minutes at a time consumes 13,000 VA at 240 volts, single phase. What is the minimum size conductor to power this up? And the answer to this question, just want to take 30 seconds to let you know what we do here at electricaltime.com. We do online electrical classes from the comfort of your home. And then we also have this free service. So if you click on the subscribe for free NEC questions, Monday through Friday, you'll get an NEC code question and an answer sent to your email. All right, so back to our video. Is B, and that is going to be 6AWG. So let's see now how we found the answer to this. So when you're looking at a question and you see VA and you see volts and you're saying, maybe this is like Ohm's law or pi formula that I have to use. But let's highlight the important information. So we're being told that we've got 13,000 VA. We're told this is going to be 240 volts at single phase. We're told that this is not a motor. So this is not going to be Article 430 for motors. And we're also told that this piece of utilization equipment is going to operate for 15 minutes at a time. So we're not looking at something that's considered to be a continuous load. And a continuous load is something where the max ampacity is going to continue for 3 hours or more. All right, so let's see how we solve this problem. All right, so first thing we're going to ask ourselves is, what article are we talking about here? And in this case, we are talking about Article 310, Conductors for General Wiring. And that's within Chapter 3, Wiring Methods and Materials. And then we're going to look at Part 3 in Article 310. And then we're going to look at my favorite table, and that is Table 310.16, Ampacities of Insulated Conductors. And in the 2017 Code Book, that is going to be Table 310.15b16. And they changed the table numbers on us. They didn't ask me if they can do that. They just did it without asking me. I was kind of surprised. All right, so let's see what we got in our narrative here. Since I did not tell you what the terminal ratings were for the piece of utilization equipment, nor the terminal ratings at the other end of the conductor, you cannot assume 75 degrees C connections for the conductors. You're going to know what's on both sides of that conductor. If one side has temperature terminals that are rated for 75 degrees C, and on the other side of what it's connected to, it's only 60 degrees C, then you're going to be limited to the 60 degrees C. All right, so be real careful about that, especially when you're taking an exam. 110.14C1A, and I'm going to highlight that here. It's very important that you understand this. So again, that's 110.14C1A requires us to use 60 degrees C rated conductors if the load is 100 amps or less. If I said that the terminals of what the conductors are connected to are 75 degrees C, then you can size the conductors to the 75 degree C column of Table 310.16. Otherwise, it's going to be 60 degrees C. Also keep in mind that certain size conductors steer us to use the 60 degrees C and 75 degrees C columns of Table 310.16. Read 110.14C1A and 110.14C1B for further clarification. And these are very important things that you must understand, before you start looking at how to size a conductor going to table 310.16. All right, so let's continue. Let's see what we got. So let's take the 13,000 VA and we're going to divide that by 240 volts to get our amps, which gives us 54.2 amps. Going to table 310.16, we look at the 60 degree C column for copper and see that 6 AWG conductor is rated at 55 amps. So 6 AWG is going to be correct. If I had indicated that this piece of utilization equipment would run for 3 hours or more continuously, then we would have been required to multiply the computed amps of 54.2 by 125%, which would have resulted in 67.7 amps, and which would require us to use a 4 AWG conductor, which are rated for 70 amps. All right, so here the answer is going to be B, and that's 6 AWG. All right, so let's take a look at the table here, and you can see, for my code book, I have it all marked up. But really what I want to show you here, even before we look at this, there's something called the NFPA link. And it's having the code book on your cell phone, on your tablet, on your computer. It's absolutely phenomenal. So go check that out. You go to nfpa.org and then you check out their NFPA link. Again, it's a really cool app. I highly, highly recommend it. All right, so you can see I have a lot of scribble in here. And let's take a look at my scribble. So I have some notes here. So, I'm reminding myself that, for the 60 degrees C over here, that I'm going to look at 110.14C1A. That's on page 48 in my code book. That's 100 amps or less. And I'm also reminding myself that we have another condition that this is 14 AWG through 1 AWG. And then I'm going to be using that 60 degrees C. All right, so now let's take a look at the 75 degree C column here. And again, we're talking about copper right now. I'm not talking about aluminum. So if we don't tell you what conductor material, that we have in the question, it's going to be copper, unless we tell you it's going to be aluminum. And here we have 75 degrees C, and that's going to be over 100 amps. And the code reference is 110.14C1B, and that's over there. All right. Again, if we don't tell you what material this is, it's copper. But if I tell you it's aluminum, then it's going to be aluminum. All right. So let's erase this here, and let's go look back at our question real quick. So when we did our math, we found out that after doing all of this multiplication business, that we ended up with 54.2 amps. And we need to find a conductor that's going to be good for 54.2 amps. And again, let me just erase this stuff here, and let's just go over it one more time in case I went too fast. All right, so we were told we got 13,000 VA, and we're told that we have 240 volts, and that gave us 54.2 amps. All right, so if you don't know how I got that, let me draw something here, which, you should always draw when you get to a question that talks about VA and volts and amps and resistance. And let me just do it here. All right, so I can tell right here that I'm going to have to use the pi formula, and that's going to be PIE. And what do I know so far? I know my VA. And when you see VA, you can think of it as watts, for the purpose of, these exam questions. They're not exactly the same, but, for this purpose, consider it to be the same thing. So I know P, that's going to be the VA or the watts. Do I know my volts? Yes, I know my volts, and that's over here. What I don't know I, and I is going to be for amps. And in this case, I is equal to P divided by E. All right, and I don't know if you can read that there, but you know what? I'm going to rewrite it down here so you could see it, just a little bit better. All right, so, I'm going to solve for I, and then I is going to equal to P divided by E. So in this case, I is equal to 13,000 VA divided by the voltage, and the voltage that we have is 240 volts. All right, so I'm going to open up my calculator and I'm going to do this math with you, just to make sure that we're getting the right numbers. All right, so we are going to take 13,000 VA and we're going to divide that by 240. And I, for amps, is equal to 54.2 amps. All right, and that's how we got that formula. So let's take a look now at table 310.16 in our 2020 codebook. And again, we're looking for an ampacity in the 60° C column for copper. That's going to give us at least 54.2 amps. And I'm looking here at the 6 gauge, and that's going to be good for 55 amps. And that's going to be our answer to this question. All right, so I hope you enjoyed this question. And again, check out the NFPA link at nfpa.org. It's a super cool app, $10 a month. I think that's what they're charging for it. And it's a really good deal. That's all I can tell you. All right, I'll see you on the next question.